Hi there, and welcome to episode 5 of the Geology 101 video series. I'm geology professor Shawn Willsey. Thanks for joining me today. And the Geology 101 video series is designed for those folks who maybe haven't had any formal education in geology, or maybe you've had it years ago and just want a refresher, or anything in between. It's really for anyone who's willing to learn the basics of geology. And this course is designed and modeled right after the college course that I teach here each semester. So it's the same lectures, the same content. The only thing missing are some of the lab and field trip experiences, but you can supplement that material through my YouTube channel with some of the other videos that are available. So thanks again for joining me. And today's episode 5, is on transform plate boundaries. As always, I'd encourage you to start at the beginning and work your way through. We're kind of building our knowledge set as we go. So if you just jump into an episode and you're a little bit confused, that might be a good point to go back and hit some of the basics and hit some of those previous episodes. So thanks again for joining me, and thanks for your support. So let's go ahead and jump in here with our first bit of information about the transform plate boundaries. So transform plate boundaries are interesting. The most fundamental plate boundaries are the divergent and the convergent plate boundaries, the ones that actually really control, as we've talked about before, plate motion. You can think of transform plate boundaries as basically being connectors. They connect either two divergent boundaries to each other, two convergent boundaries to each other, or one of each to each other. And so these are interesting plate boundaries. They're most commonly found in the oceans, but we do have some on land. They have purely horizontal motion. So their motion across the plate boundary is horizontal. And if in a perfectly textbook transform plate boundary, all that motion is side to side or horizontal. So these plate boundaries would not give us, and again, the classic textbook sense, big mountains or deep trenches in the ocean like we see with the convergent and divergent boundaries. However, that being said, we will see that you rarely get a case where a transform boundary is, perfectly horizontal motion. Usually there's a little bit of other motion involved, and so we do get topography and we do get some interesting landforms there. So they do produce earthquakes. The two plates of crust, whether they're ocean plates or continental plates, are sort of in this locked status for much of the time. And as that tectonic stress builds across the plate boundary, that ultimately can manifest itself as motion, quick release of that stress that's building up across the plate. And that's what we would experience as an earthquake once that stress is released. And we can see earthquakes up to sometimes as big as magnitude 8. And so these are some of the more, where they occur on land anywhere, some of the more deadly fault systems we know of in terms of just threats to civilization. So you can see up here in the top diagram, two divergent plate boundaries. So here's a divergent plate boundary out in the ocean here. You can see the motion on either side. Here's another one on this side. And if you look at a Google Earth image through the ocean or any plate boundary map, you'll see that these divergent plate boundaries that run through the ocean, there's not one big feature. They tend to zigzag. They're offset. There's lots of little segments, and that's because the rates at which they're spreading vary to some degree. The Earth is a curved three-dimensional sphere, and so we just end up with these offset segments. And the thing that allows this plate to move past the other one on this side, so notice that on this side, this plate at the top of the diagram here wants to move to the right, but on the opposite side here, this lower plate boundary wants to move to the left. And so you get conflicting motion, and the transform plate boundary, that sideways horizontal motion, is what allows those two sides to slide past each other. So the transform plate boundary would just exist as a connector between this divergent plate boundary and this adjacent one here. And then this diagram here at the bottom left is just showing you a very simplistic map view of a divergent boundary here on the left. And then when we draw these plate boundary maps, we often draw convergent plate boundaries with this sort of symbol here. We don't need to get into the details here, but just pretend this is a subduction zone. Here's a divergent boundary, and then the transform boundary would just be the connector between the two. And so there's lots of good examples of these, the San Andreas Fault probably being the most preeminent example, perhaps the most studied plate boundary or fault system in the world. The Dead Sea is another great example, and the Alpine Fault in New Zealand. And we'll hit on a couple of these with a little bit of detail. We obviously could spend a whole video deep diving each one of these, but I want to give you a little sense and a little flavor of each one. Let's jump to an animation here first that might help us understand these plate boundaries in a little bit more detail. So let's start with this one here. Again, just a nice simplified animation to show us exactly what's going on. So you can see in this case, four divergent plate boundaries or mid-ocean ridges underneath the water here in this animation. The red shows where they are volcanically active, where we get magma coming up along the seafloor. We can see that these four divergent boundaries are offset. And so what we'll see here as we run the animation is we'll zoom in to a little section of these here, drop down, and then watch as we have this divergent boundary here, this one here, and then the transform plate boundary would be between those two active sections of the divergent plate boundary. So the animation's nice, it's very cartoonish, and it's very simplified, and it shows this plate on the bottom of the diagram moving to the right relative to this one here and accommodating the motion. Of course, the big lie in the animation is the sort of conveyor belt style that it shows this. It shows the plates just moving along, doing their thing, just sliding past each other, when in reality what's happening is those plates oftentimes aren't moving. There's stress accumulating, it's a very frictional surface, and then finally that stress is overcome with movement, and that's what generates the earthquake. But nonetheless, the animation nicely shows more or less how these work. So that's what they look like under the ocean. We can also get these types of plate boundaries occurring on land. And let me go back here real quick. Where we see these on land, we might see these occurring where we have some sort of linear landform or other feature that crosses the plate boundary. So in this case, this is the transform plate boundary here. We have a mountain range, a continuous mountain range across that plate boundary that formed earlier. And as the plate boundary moves the two plates in opposite directions, will generate earthquakes. That's what the little explosion symbols are there. And then it will offset over time this once continuous mountain range. And so the idea here is as the earthquakes occur, the plates move those two mountain ranges apart, and now they look like two separate mountain ranges. And it took some detective work from those early geologists to go into these mountain ranges and find these geologic similarities that allowed them to construct what these areas look like before the fault motion. Remember, plate tectonics is a fairly new idea. So before, let's say, the late 50s, early 60s, there wasn't good explanations as to why we would have similar rock types, maybe similar mineral deposits in very discontinuous areas. But the plate boundary here and the idea of plate tectonics helps put those together in a little bit more better way. So hopefully those little animations were helpful. Let's go back to the PowerPoint and show you a couple other images here. So we've talked about this here. Let's look at the San Andreas Fault in a little bit more detail. Here's what it looks like from the air in places. It, of course, doesn't look like this everywhere, but in places it looks like this is this linear crack or fracture running through the landscape here. But notice over here on the right, this is a little bit better. Let me make my little head a little smaller there. This is a little better map of what exactly the San Andreas Fault does. It's really a connector from these divergent plate boundaries in the Gulf of California. The San Andreas Fault, in essence, starts right here near the Mexico-U.S. border, goes up through California lengthwise, and then off the coast of Northern California, it terminates where it connects with another divergent plate boundary up here that separates the Pacific plate from the Juan de Fuca plate, this small plate here that is being subducted beneath the Pacific Northwest of the United States in Canada. And so that's what the San Andreas Fault is. It's just this long connector piece, between these two divergent plate boundaries. Um, in some places, it looks like this. So in places where we can see it offsetting, in this case, a stream channel, excuse me, we can see this stream channel has been offset over, let's say, a few thousands or hundreds of years, some period of time. And so we can actually see the plate motion across the plate boundary here. So in this case, as we look across the fault, the motion is to the right. Everything is apparently moving to the right. And it doesn't matter which side of the fault you stand on. As you look across the fault, that's the way things appear to be moved. And we'll talk more about that when we get into fault types later in this Geology 1 video series. So we can see transform plate boundaries best from above, where we can see that they have offset features that were once continuous. Could be spreading centers in the ocean, could be streams, could be mountain ranges, could be a fence, a highway, whatever the case may be. So to understand the San Andreas Fault in a little bit more detail, let's check out an animation that was put together by Dr. Tanya Atwater a number of years ago that nicely shows how the San Andreas Fault evolved over time. And this, again, could be a deep dive we spend a whole video on, but let's just treat this somewhat briefly for the sake of this video. And so what you can see here with this red kind of zigzag line in the ocean here, this is the plate boundary that would have existed about 35 million years ago. Notice there's a time scale on the right going from 40 million years to the present. This plate here is the North American plate. Then we have the Pacific plate on the left side, but in between the two, we have the Farallon plate. So this is a plate that mostly no longer exists, but played a huge role in the geologic development and evolution of Western North America. Again, a subject for another video at another time. But what we're going to see here is this divergent boundary between the Pacific plate and the Farallon plate sends the Farallon plate smashing and colliding with Western North America, where it is subducted along this plate boundary shown with the little triangles along it. Notice that the states here in Western North America look a little different, like Nevada looks really squished, and even California, things look a little bit wonky here. And that's because once the San Andreas Fault becomes a little bit more developed in the more recent time period, that's going to actually stretch those states out. Remember, there's another episode here of what's called basin and range extension that's going to stretch these out. Again, that's a subject for another time. But I just wanted to show you the development of the San Andreas Fault over time. So it does not exist here right now. So at this time, there is no San Andreas Fault. We just have a subduction zone and a divergent plate boundary. But once this plate, the Farallon plate, and this divergent plate boundary starts to be consumed or subducted beneath Western North America, that's going to usher in the birth, if you will, of the San Andreas Fault. So here we actually have the San Andreas Fault in this little section right here. Here's one fragment of the Farallon plate. Here's another one to the south, and we're going to see this incipient San Andreas Fault actually lengthen over time as more of these two plates get subducted beneath North America. So let this roll a little bit further. We're almost to 20 million years right here. The other interesting thing you're going to see happen here in a second is notice that the plate boundary, so now the San Andreas Fault is quite a bit longer, but what you're going to see is this plate boundary, which started on the western margin of Baja California, it's actually going to jump, geologically jump. It's going to move quickly from this offshore setting on the west side of Baja to where the present Gulf of California is. And again, that's the subject for a completely another deeper dive. I did my master's research down in the Gulf of California, so I could do some videos here at some point on more of what's taken place there over the last 15 million years or so. So we'll just watch this a little bit further. The plate boundary, there it goes. Now it's in the Gulf of California. So now Baja and coastal California, which were once part of the North American plate, now they are firmly attached to the Pacific plate. And the San Andreas Fault effectively runs from the Gulf of California up through coastal California and to near Cape Mendocino here in Northern California. There's this little funny area in here. This is the transverse ranges, and there's sections of Southern California where things got rotated, and it's kind of complicated and beyond the scope of what we're talking about here. But I just wanted to show you a little bit of how the San Andreas Fault evolved over time. So hopefully that was helpful. And I'll make sure I put a link to that in the video description if you want to take a look at that. So let's turn back to the PowerPoints as we continue on with our discussion of transform plate boundaries. And let's look at one other place where we have this type of plate boundary, and that would be the Dead Sea over in the Middle East. So here I've got a nice satellite image. Here's the Mediterranean Sea, the Gulf of Suez, the Red Sea, the Gulf of Aqaba. This is the Sinai Peninsula. But this linear trend that runs through here is the Dead Sea Transform Fault. So it runs up through the Gulf of Aqaba, through the Dead Sea and onto the Sea of Galilee, if you know the geography of that area well, and it separates these two plates. Now these two plates are actually moving in the same direction. They're both moving to the north or northeast, but the Arabian plate is moving so much quicker. This plate's moving so much faster than the other one that that the relative motion is set up like this. So the African plate's not truly moving to the south, but when we use these arrows as relative plate motions, this one's moving faster. It's just like if you and someone else were walking down the sidewalk in the same direction, but the other person's walking faster than you, they would walk past you, and it would appear as though you're moving apart from each other, right? So it feels like if they look kind of over their shoulder, looks like you're moving backwards because you're moving slower, even though you're moving at in the same direction, but at different rates. So that's relative motion for you. But this is another example of a transform plate boundary. And again, for another time, we could talk more about the Dead Sea and why it's so low below sea level. But we'll kind of get to this a little bit as we turn back to the San Andreas and talk a little bit more about that. So recognize, as we've finished with these three different types of plate boundaries, divergent plate boundaries, convergent plate boundaries, that's episode 2 and 3, I believe, or 3 and 4. And then now with episode 5, this episode, transform plate boundaries, realize that you can have combinations, right? Plates can move past each other, like transform plate boundaries horizontally, but also move a little bit apart. So there can be components of both divergence and transform motion that happen together. It stands to reason that you can have a little bit of both. Similarly, you might have transform motion, but a little bit of convergence where the plates are moving towards each other. And so that's important because that sets up some of the interesting landforms that we see in some of these locations. You might say to yourself, well, wait, if Southern California along the San Andreas Fault is purely transform, we shouldn't have any big mountains. There shouldn't be any real differences in topography. And yet when we look at that area, there are mountains in Southern California that go up over 11,000 feet. There's an area in Southern California that's below sea level in the Salton Trough area around Palm Springs. And so we do find evidence of both of those there. So using the Gulf of California as an example, so this is an oblique divergent plate boundary. So most of the motion is this transform motion where Baja California, this peninsula, and the western part of Southern California attached to the Pacific plate are all moving to the northwest relative to the North American plate. So this plate's moving much faster than this one. Is the rest of North America really moving to the southeast? No, not at all. In fact, it's moving to the west, but this plate's moving so much faster that sets up our relative motion there. But in addition to that, the other thing going on is that the plates are spreading apart. So there's an extensional component of motion as well. It's not just sideways. It's like you sliding your hands past each other, but then also moving them apart a little bit over time. And so there's a sort of scissor type motion. And so as this continues into the future, we would expect that the Gulf of California would get longer, it would get wider, and eventually the ocean water here would encroach into western Arizona and southeastern California, that it would extend not just into Mexico, but up into the US as well. And so this is our example, or one example of an oblique divergent plate boundary. And if you look at here's just a plate boundary map with some Google Earth imagery here. If you take away the red lines in here and just look at a Google Earth image on your own, you'll see lots of straight linear trends in the Gulf of California where we have these different types of plate boundaries. So these little tiny short segments, those are the spreading centers, those are the divergent plate boundaries, and they're connected by these long thin lines which are the transform plate boundaries. So you can see these zigzagging through the Gulf of California. Maybe I'll show you those real quick here on Google Earth just while we've got this open. Oh no, I gotta go there real quick. Let me just grab this real quick, Gulf of California, and drag this over here for you. So you can actually see those pretty nicely as we go into the Gulf of California. So you can see on the imagery here lots of these interesting straight lines that define these divergent plate boundaries and these transform plate boundaries. As you move up the Gulf, though, interestingly, once you get past these two big islands here, let's say, you kind of lose it. You don't really see those same trends as this plate boundary transitions from the ocean onto land, and that's primarily because the Colorado River has a huge delta here and has been pumping vast amounts of sediment into the Gulf of California over the last, well, at least 6 million years or so, and has filled in filled in a lot of that topography. So think of the Grand Canyon, right? Where did all the rocks and sediments that used to be in the Grand Canyon, where did all that eroded material go? Much of it was transported down the Colorado River, dumped into the Gulf of California. Some of that sediment moved around by currents and stuff, and that's why you don't see those nice linear trends like you see down here further in the Gulf of California. So fun little side note there for you. Okay, so the last thing I want to do here to wrap up this episode, and hopefully this has been helpful to you, is this is new for me. I got a new little, well, it's not new. I borrowed it from down the hall. So let's see if I can do this okay. I want to draw for you how these plate boundaries can dictate the type, how the plate motion and the geometry of the plate boundary can dictate what actually happens. So if we look, for example, in Southern California or other places, we see that the San Andreas Fault is not perfectly straight. So if we have it coming through here, then a little bit of a bend, and then it goes like this, okay? And if we put our plate motion arrows on here, vectors, right? So if the plate motion is, if this plate, let's just make this hypothetical, plate A and plate B, okay? So we have two adjoining plates, okay? And if the relative motion between these plates is as such, then right here in this area, we'll have a perfect transform plate boundary. Same thing up here. Plate boundary and the vector is moving to the northwest in this case. This plate's moving in the opposite direction. So these two areas would be nice, well-behaved transform plate boundaries. You know, horizontal motion, earthquakes, but no real interesting topographic features. Well, what happens if the plate boundary has a little bend to it, like this? What actually would we see there? Well, if we keep these plate motion vectors, these arrows, and just draw them exactly like I drew them elsewhere, we can see that in this little zone here, we would have extension. The plates would actually be pulling away from each other. And as we've seen in our previous episodes with divergent boundaries, this would produce crustal thinning, so the crust would get thinner. This would promote the generation of magma and volcanoes. The topography would be lower. And this is exactly what we see in Southern California at the Salton Sea. The Salton Sea sits below sea level, the Salton Trough, and because it sits more or less in one of these bends in the San Andreas Fault, Gulf of California plate boundary system. So the whole point here is it's a perfect transform plate boundary, but in this zone here, it would be an oblique divergent plate boundary. And the same thing can occur, or a similar thing can occur, if we have the plate move in an opposite direction. So now instead of a bend that as we move along the plate bends to the right, what if we take that same initial setup, excuse me, and have it bend to the left? So now add our little arrows, okay, plate A, plate B, okay. Up here, happy transform fault, everything's okay. down here, happy transform fault. The plate motion, the arrows are parallel to the plate boundary, so everything's great. But what about in this area in between? Well, draw your arrows like this, and notice now the arrows are pointing towards each other. We have collision. And so we would expect in this zone, if this is continental crust, like Southern California, we would expect there to be uplift, mountains, crustal thickening. So we're thickening the crust. Excuse me. And so our topography now is actually higher. And so this is what you might expect in this kind of region. And this is exactly what we see, excuse me, getting over a cold, in Southern California in places. So with that, we'll go ahead and sign off. Hopefully that was helpful. Just a little discussion on transform plate boundaries. And we'll see you next time on the next episode.